This will be the recorded description of the PillsburyW Shimmick case, and this is what I'm going to show is a compiled PowerPoint that contains pieces of all of the graphics that we did for this case, which were there's probably 20 or 30 of them, separate animation sequences. I've combined them here to make a summary story so you can access the entire sequence with this presentation. Hopefully it'll be useful for other demonstrations to clients in the future. So this case involved a construction delay case involving changes to the Golden Gate Bridge. The initial plan was to add a suicide deterrent system to the bridge, which was this net that runs the entire length of the bridge on both sides, east and west side. So it makes it very long and very complex because there's a million parts to be added here. There's net support arms in the nets and all of that stuff. So that was the primary goal of this project. Secondarily, while they were in the process of doing that, there was other maintenance and repairs that they were going to do to the bridge while the crews were out there. I'll discuss those in a moment. We represented the joint venture that contracted to do this job, a group called Shimmick Danny's joint venture, and our primary client was Shimmick, which was the engineering company that designed the equipment to do this, planned to do it, and turned out that they couldn't do it as planned because of a number of things that were beyond their control, and that's the source of this case, and we'll talk about those things that caused this complex sequence of delays and cost overruns. So this photo just kind of give you a general idea of what was intended. As an overview of the bridge and a way to identify the parts, we have a nice 3D model of the bridge that we used in many places on this. The bridge basically runs south to north across the entrance to San Francisco Bay. The bridge is divided into what they call spans, that are the segments between the south, they call it the back span or span 1. Span 2 goes from the south tower to the middle of the bridge. Down here, span 3 goes from the middle of the bridge to the north tower, and then span 4 goes from the north tower down to the shore on the other side. It's interesting to note that on the span 4 here on the north side, the bridge gets real close to the rocky shoreline, and that limited access to getting under the bridge. The joint venture's plan was to put a temporary work platforms called travelers that would move underneath the bridge to give them access to all the places they needed to work. And their initial plan even worked under here, but some of the changes that the district made, the owner of the bridge made that impossible and caused them to have to do some workarounds. So there were another number of other things that caused workarounds as well. So anyway, just a kind of a broad view look at the bridge and how it's named. We'll run the animation here and kind of zoom into a close-up so we can look at more of the details of the bridge. These sections are 25 feet long. Of course, there are thousands of them. The area along the bottom is called the bottom chord, and we'll talk about that a lot because that plays a role in the equipment that had to be used to work on the bridge. This other's parallel section on the top of that is called the top chord, and of course the roadway and the suspension cables. And all this is, I think it's a couple hundred feet off the water at the middle of the span, so it's pretty high up there. The joint venture created a work plan to do this project smoothly and efficiently, and get this done for the budget they proposed. And their plan was to add some temporary travelers. So we'll start with the bottom temporary traveler down here, which is a big work platform. It's a big scaffold system that was going to hang on the rails. There's rails under here that carried the old travelers. They're going to hang this on the rails. It's free to move left and right. It's got its own electric motors in it. And from the bottom platform, they can put on the net supports. They can replace the bottom rails. They can replace some of the interior rails, and they can eventually put the nets on. The side travelers, which are independent but will move together with the bottom travelers, can access all the work that needs to be done on the side. They're going to replace a pair of rails here that will hold future travelers. And then on the west side, they're going to add wind fairing, block the wind coming in from the ocean, and then replace the handrail on the west side of the bridge. So all of that work was planned to be accomplished with this set of travelers, and they could move independently, or they could move. They moved together, but they had their own electric motors. They could move when they needed, which meant that the work could proceed at the night and day, and they weren't dependent upon access from the roadbed, which meant they didn't have to stop traffic. Here's a little closer view of the parts that needed to be replaced. So we faded away a chunk of the bridge. The bottom traveler rails or traveler beams were going to be replaced. So those were at the very bottom here. Inside the bridge, there's another set of rails that an interior traveler rides on. Those were due to be replaced. On the top chord of the bridge, shown in close-up here, are little metal brackets that they call rail chairs, which are attachment points for the side rails that are going to go on the bridge. So they're spaced every 6 feet throughout the length of the bridge, which makes about 2,000 of these throughout both sides of the bridge. And then the side traveler trolley beam and the crane rails, which sit on those rail chairs, were set to be replaced. And then over here on the west side, a wind fairing that kind of blocks the wind from coming across the sidewalk, and new handrails. So all of that work was, and then of course the addition of the net supports. And the traveler system was designed to not block that, so that the bottom traveler could facilitate the addition of the net support, and the side traveler wouldn't get in the way while they did the work on the rails and so forth above it. So that was the plan, and it was a good one and an economical one. Here's kind of a big picture of those travelers in place. There's 5 of them that were used. They were the temporary work platform, so you can see them hung under the bridge in 5 places. So the plan was to work on all of the spans simultaneously. As I described before, this flow sequence could happen smoothly and economically. I did a little animation here, a sequence that demonstrates that work. So go back up here to day 1 of a typical work span. They install 25 feet of side rail up here on the top chord. On day 2, they continue work on wind fairings, handrails, and underneath here on the bottom rails. And on day 5, they move the side traveler over just a little bit so they can install another 25-foot section of side rail and then they put the net supports on and finish up the underneath work with the new rails on the bottom and the interior, along with the other wind fairings on the west side. And then on day 10, they move them all forward. And as the time lapse shows, this happens during the daytime. There's no disruption to traffic. Work could also proceed at night if necessary. And that was a good plan, good way to do it. Here it is just run this as a little movie. We put it all together, so it kind of jumps pretty quickly as a time lapse, but it shows this sequence of move, work, move, work, move, work without interrupting traffic. So that was a plan to move down the bridge section at a time, do everything you need, do all the changes. the only work that was planned as the last pass was to come along with a reel of net material and actually string the nets on this. But that had to wait until all the net supports were up. So that was just the final finished piece to this thing. Got a couple of views of the underneath side. These work platforms were very large, very heavy, and they could provide access to both sides of the bridge so that they can do those all at once and leave behind them a trail of new net supports here ready for the new net and all the new parts. So that was the plan. Then it all went bad. So I'll mention this. I put this note in here so that if you're trying to present this, you can have a reminder of what things went bad. So the first thing that happened that after the contract was signed, the joint venture Shimmick did a field verification. They went out on the bridge and started checking the condition of the bridge, and they found out that the bottom rails were so badly deteriorated that it was too weak to support their proposed bottom travelers. Those new, so anyway, those rails wouldn't work as planned. So the workaround was Shimmick designed a new bottom traveler that used brackets that hung from the bottom cord, and I'll show you plenty of pictures of that. And that would hold the bottom traveler, but it was a cumbersome process. It was no longer automatic. The traveler couldn't move by itself. It had to have those brackets moved manually by cranes that were parked on the roadway, which meant that they had to block traffic, which meant that they only could do it at night when there was less traffic interruption. So that was kind of interruption number one and workaround number one. Then secondly, during this period, the bridge owner demanded for a number of reasons that these work platforms, the travelers, all now support 4 times their dead load rating, which is just the weight of the traveler, just for safety reasons. The previous specification was only 1 times the dead load, and of course now that meant we had to design entirely new bottom and side travelers, making them all heavier. And Shimmick's design for the workaround up here with these brackets would handle the weight of the new heavier bottom traveler, but that meant they couldn't use the side travelers now. And so the side travelers had to be replaced not by mobile self-moved things, but by fixed platforms that again could only be installed and moved at night by cranes on the work deck. So that was kind of wrench in the works number 2. The third problem was that during their field verification, they found out that those rail chair, the drawings that they were given for the new rail chairs didn't match the hole patterns on the bridge. Somebody relied on drawings from the 1950s when the original rails were installed, and those were not accurate. The bridge had actually a whole variety of different things that were probably put in by hand, and that made the owner have to go redesign those rail chairs, which put another delay in the works. And then finally, for the new travelers, when all this work was done, the contract provided for making new maintenance travelers, both the bottom and the side one, and the owner insisted that these be made entirely from American-made parts, which was, might be okay, except that the specifications for these travelers required sizes or parts of certain strength in certain size, like motors, that had to fit within the small confines of these travelers, and those components, not all of those components, were available from American manufacturers. So that threw another delay in the works. So let's go through and look at these, starting with deterioration. Underneath the bridge, there was lots of rust, and that, survey revealed that a lot of this stuff needed to be replaced, which could be done, but it weakened the support system for the maintenance travelers. So here's an example of that. It's pretty nasty in some places. Here was a particularly bad one. We're under the north span number 4, looking down at those rocks on the north shore, and some of the lacing bars are completely gone and just piles of rust flakes here. So it was in bad shape. So this known, that meant that the contractor couldn't rely on those structures to hold up his work platform, so they started the workaround process. So here's the temporary bottom traveler. So this was workaround number one. They, instead of, we couldn't rely on the rails under here, we had to put in these red brackets to hold the traveler, and these brackets had to be on the bottom cord on both sides of the bridge, which was fine. It was strong enough to hold it. We had to then go through a very elaborate and painful sequence of, when the time came to move this platform, it couldn't move until the brackets ahead of it were installed and the brackets behind it were removed. So we did a sequence of animations showing that step. So I'm going to back up here. During the daytime, traffic was running. They finished their work, and now this work has to proceed at night. So they have to block traffic, bring in a series of cranes and trucks and barrier trucks to lift these brackets off of the bridge. These are the ones that are behind the work platform. Lift them off the bridge, put them on a trailer here, on a flatbed trailer, and remove the brackets on this side. The next that was one night's work. This is daytime again. Then on the second night, we bring in the same set of brackets and install them on the where we're going to move the platform to. So that's night number two. Truck comes in, they install those brackets. Go back to daytime on the third day. Then we move this around to the other side of the bridge, because now we have to move those brackets that were on the opposite lane. So they, for the third night, they come in and remove those brackets, put them on the truck. That takes all night. Clear away, go back to let traffic run during the day, come back on the fourth night, and install those brackets in the direction that the traveler is going to move. Again, with a minimum of 4 trucks here and lane closures in the middle of the night. And then finally on the 5th day, that bottom traveler can move forward to its next section, so they can work on the next chunk of the bridge. And that whole sequence repeats forever and always. It was incredibly tedious. So now, here's the second workaround. Now that the owner insisted on the work platforms holding 4 times their dead load, the workaround was to do fixed platforms that were strong enough and didn't rely on the rails. These could hang from the top cord, but they had the same kind of problem. They had to be installed from the road deck at night with trucks that required lane closures. So we've got a similar sequence for this one, showing that here's a night lane closure. We're going to take these 2 of these work platforms off the flatbed here and install them on the side of the bridge. And this is the onset of a massively complex sequence. This is just day 1. They can install 2 of those pieces. And then same night they can come in and drop in the in-between smaller platforms that'll fit in the slots left by the other 2. Got to go to daytime now, and then come back the night of the second day and install 2 more of these. I'm just going to click through these quickly. And on the third day, they come back and install the in-between platforms. 4 days later, because they're doing this again in other sections of the bridge. On this one, then they come back in 4 days. So on day 8, they come in and install another section of 2 of the big platforms. Wait a day, have to come back into the fill in the in-between section and get that whole sequence, that whole span ready to work. And then they leave that in place for 21 days so that the workmen can do all the work they're supposed to do here. They got to replace rail chairs, rails, two rails on this side, and they got to replace the same rail, chairs, rails, and the wind fairings and the handrails on the other side. So that takes 21 days in this section. And then on day 22, we begin the process of removing these platforms, taking them out in sequence with breaks for daytime traffic, come back and process this sequence at night. The goal here was to demonstrate that the changes made by the owner in insisting on these heavier platforms caused this immense amount of manual labor that took nighttime work only, required lots more men, lots more trucks, lots more cranes, and a huge number of days to get this thing done. So we'll get through this sequence so that we can see that this span of 1, 2, 3, 4, 5, 6, or 8 sections on the bridge, by the time they can get all the work platforms off of there, it's, I forget, 60 some days for just this section, and then they're ready to move on to the next one. So it was a tedious animation, but it also demonstrated the immensely tedious process that was forced on our contractor by the changes that by not only the condition of the bridge, but the changes that the owner made in midstream. Then we found that the design for the rail chairs didn't match the holes on the bridge. So here's a little close-up section of this. The plan was to remove about 12,000 feet of the old rails on the top, and then a similar length of the trolley beams on the side, and remove those old rail chairs, which are nearly 2,000 of them, and install the new rail chairs, which were designed by the owner. And lo and behold, we find out that they don't match the hole patterns. So work had to stop while they looked at, they redid this survey and looked at where all the different varieties of rail chair lived along the length of the bridge on both sides. Here's a close-up of the workman removing one of the rail chairs. Here's the chair. You can see where the rail was on top of it, and here's a missing chair, and it happens to have a particular pattern of holes, but that's not a constant pattern. That changes throughout the bridge. So we did this little tutorial that shows, for example, here's base plate number 4 for a particular chunk of the bridge. If you bring in that contracted base plate and try to fit it, well, we can line up that top hole there, but the rest don't line up. We can move down here and try to line up that hole, and well, that lines up, but the other 3 don't. And we can try that one. No, we can't find one that matches all of them, so that's a bust. We can't install that plate there. We, after a period of time, once the owners redesigned that base plate, they came up with a plan that had they came up with a variety of plates that would match any bolt pattern on the bridge. So the plate was a little different shape, had a couple different holes, and then they used clamps on the back to hold it down. So that gave a better fit, but it took time to redesign that. And of course, our guys had to then go back and install that. So here's another pattern where we got a type 2 base plate with wider spaced holes, and the B-line clamp business would fit any spacing on the B-line hole. So they finally did get a system that would work, but that was after some delay, and then have to go back and install it. And here's an actual photograph of one of those installed on the bridge with the back clamps and a fresh coat of paint. There were all of these different varieties and different hole patterns that were identified, different sequences throughout the bridge, and we showed as a summary here that those things do fit, and that finally was the answer to that question. And then the final delay causer was this issue about building these new travelers. These are the new ones that are going to go in place, that are going to live there for years now and become the maintenance travelers. All of all four of these had to have, according to the owner, be made from American-made parts. But due to some of the mechanical specifications and size problems, these couldn't be had by American manufacturers. So they were broken into two categories, the mechanical and the electrical. So here's all the mechanical stuff in blue that was needed to fit in the space available and had the strength and properties required for this structure. These are all the ones that couldn't be bought from American-made manufacturers. And then secondarily, there were a ton of electrical components that were, mostly foreign-made that just, American manufacturers didn't make that met the specifications required. So there's, lots of electrical components that we highlighted here. And when you put them all together, you can see the extent of the delay caused by this, and you got to go through every one of these and find an alternative supplier, and I'm not sure that's done yet. So kind of the final wrench in the works. So those were the things that caused the massive delays in this business, and the heavy workaround that took a ton more time and money. And then the final thing we put into this was a demonstration of an interactive demonstration of what the delays amounted to and how they compared with the as planned compared with the as built. So this was another one of Sean's super interactive data displays, kind of like Johnson, UDOT, and that sort of thing. So we've got our standard timeline down here at the bottom with key time spans in the works here, showing what the as planned period was in green, and the various reasons for delays caused by either conditions on the bridge or owners' changes. So let me break down what this does, because it's a very complex thing, and I think the clients really liked it. I don't know if it ever got used, but it's kind of the ultimate summary of why this took so long. So again, here's our side view of the bridge, so we can identify where we're working. The middle drawings here are looking straight down. They're plan views of the bridge and the roadway, and we're going to color code these with the various work scopes. So the handrails will be this blue-green color, the wind fairings are light blue, the side rails are dark blue, the net fabric is orange, the net supports are bright orange, and the bottom and interior rails will be a yellow line. And the as planned will show, of course, it'll finish sooner than the as built. So let's drag into this, and as we start populating, we can see we just symbolically represented the position on the bridge. We just drew the line out here in space. So the handrail is growing along here as the yellow bottom rail are growing. The little black dots are the traveler positions on the bottom traveler. So as we move through time, those travelers move ahead, and we see the work progressing to fill in each of the spans of the bridge. And by the time you're done, we get down here to the end of the green bar, which is the as planned section. We see the full spans. We got a handrail and a wind fairing along the outer side here. We've got all the rails, side rails, net supports. All that stuff is done throughout the length of the bridge, and we're still down here fiddling with the as built, because the as built now is not done and won't be done for quite a while. So as you drag through time, you can go to any particular day and look at where the work has progressed and see where it's finished. So when you're finished, you got all the color ribbons are complete, and where the as built is still working and still fiddling around because of all those delays. So kind of a top level summary. This is not quite finished. We were getting ready to do one more pass because there's a few little cleanup items that that could be done. For instance, there's a couple of gaps here that we never did figure out. We didn't have the time to finish it. But the general story is well told, is that when you start, in 2018, and the as planned was to be done late in 2020, we can see that project went smoothly, uniformly, based upon that initial design that the joint venture proposed. And down here in the real world, due to the deteriorated condition of the bridge and the changes imposed by the owner, they're still fiddling around with the as-built construction. So that's the end of PillsburyW Shimmick.